Welcome, folks. Sorry for the delay today. It was quite a challenge to find the new room, but we have a new room. If we end up liking it, we can definitely stay here for the future. I will just have to reserve. Josh, do you mind logging into Zoom? Thank you. So, welcome all to our third class of the Coming Up to Speed summer course. Today we continue with math. We're going to be talking about more differential equations, and I'm going to give you an introduction to linear algebra. We're going to expand on that introduction on Wednesday. And today I have a very fun activity. We're going to play with shadows, and I just check and I can actually turn off the lights of this room, so we don't even have to leave the room, which is great. So as we always start, remember the code of conduct and to be nice to each other and to your own self. The usual reminder that you have all of these resources available for you. We have the forum. I have seen many of you introduce yourself there. I actually saw a cat. I'm very happy to have seen a picture of a cat. And we have the YouTube channel. I was able to upload the lecture from last Wednesday. And I hope that between Josh and I, we're going to be able to keep that up so that any lecture that you miss, you can see the end. This is a summary from what we saw last week. Let's say second lecture, we talk about Taylor series and how to visualize them as how an ant will look at a function that you're trying to approximate, that local, relatively smooth behavior. We talk about the analogy to what happens with flat earthers, that they're only taking the first or the second order. They're ignoring the second order of the curvature of the Earth, why the thing is flat. And then we talk about differential equations, and I gave you this intuition that is like the rules of the game. I don't think I went too deep into this, but I like to see it similar to if you were describing chess versus soccer. They have different rules, so they become different dynamical systems. And just by changing the rules and the initial conditions, you will see how things change as time progresses between those two. And we talk about the differential equation for Newton, whenever you're trying to solve classical systems. And we talk about the differential equation that is a Schrodinger equation for quantum mechanics. And we did an example, an in-class activity, where you actually solve a differential equation through something that is called finite element or Runge-Kutta or shooting method, has different names, but you were able to propagate an initial condition of your equation following the rules of the game, and you were able to make that curve in there. The final reminder, remember the two differential equations that I want you to commit to memory, and here I'm putting only one, and I use the palm tree visualization to show that this thing can be literally anything that you put in there, and if you're creative enough, you can even put a matrix in front of that f, which is what happens in quantum mechanics, and the solution will still be e to the stuff times your variable. Any questions or comments with respect to any of this summary from last class? And Tessa, or anybody else that is in Zoom, please feel free to unmute yourself at any time to make comments. Any thoughts, lingering questions? Is all understood and happy? By the way, when I ask that, if later in the future you do come up with a question, you can ask it. It's not that this is the only and last time that you're able to ask that. I want to make a point because actually he's not here. I forgot his name. Daniel, thank you. He made a point last week that whenever we calculated this using the shooting method, we didn't arrive at the number 12, which is what I have calculated before. And it is a really good point, and I wanted to bring it back with a numerical example. What we did was shooting straight lines. And you see, between these two curves, I have the exact exponential that you could solve by pen and paper. And I have now, for real, the approximation that you will obtain if you do exactly what we were doing. And you see that it starts accumulating error and starts deviating from the true solution. In this particular case, because your solution is convex, concave, I always forget. The solution looks like a smile, always, then your method will always undershoot, and that will accumulate to keep undershooting more and more. To solve that, what you can do is to make that distance delta x that we were taking as steps of 1, make it smaller. But you will always have that, you will always carry that numerical error in any numerical solver that you have for your differential equation. And I think it's very cute that the blue points actually match more or less to what you folks were able to calculate. So it was not an error on your side. It was the fact that I only have a finite number of you, and I had to space you with that delta x. This is the playground for the first day and the playground from the second day. Any of you have any comments? Have you tried it? I still need to figure out a way of not discourage you, but at the same time take some sort of attendance on playgrounds so that I can give you a nice certificate at the end. But anybody has any comments? Do you try it? Do you want to ask? Do you want to share?
General
Please.
question. Is the goal for the playgrounds to be do the class after they're like given, or is that kind of like is that the recommended sort of timeline?
I will, if I were you, I will try to attack them within a couple of weeks.
Okay.
So since this is not graded, I really don't care. You can come the last day of the thing and tell me, Pablo, I did all the playgrounds. Here you go. Fantastic. But it's more like a way of you taking away ideas, trying at home. If you want, share it in the forum, come back, say, I did try this and it didn't work and I don't know why. And then we can sit and take a look. I totally believe that you can go through the entire course and not do a single one of these, probably except the podcast. The podcast is very important, and you will be fine. But this, I think, will help you reinforce the ideas even more. Not only that, the ones that are coding, if you save those, that can help you in the future whenever you see the actual courses and the homeworks. So very loosely define it. Give it a try if you can. I'm here to talk about it if it's helpful.
Okay, thank you.
And if you do them, you just need to tell me that you try them, and you will get a sticker in your certificate, and I'll give it to you. Okay, so beyond that, any other comments or questions with respect to these things? Very good. So we continue. We're going to start lecture 3. So we went through the summary of last time, and for today, we're going to talk about differential equation, a couple of actual examples that I want to solve with you, and then we're going to have a class activity where you're going to solve some quantum mechanics without even knowing quantum mechanics necessarily, because we haven't talked about quantum mechanics yet. We're going to have a break, and then we're going to start with linear algebra. And in here, we're going to have another activity. And I didn't do this, so you're not going to have this for later. Okay, so for differential equations that we were talking last time, I want to put them in practice into solving something that actually, wait a minute, because I don't want my laptop to, to solve something that actually looks kind of like what you will encounter in courses or as a physicist, scientist in general. The example that I want to give you is the pendulum, and we're going to go step by step on how to solve that equation. So I am trying to describe a dynamical system in where I have a mass m attached to a rope, and that friend is going to oscillate back and forth. How do I know that it will oscillate? Well, we have done that in your life. You probably have played with something like that. Somebody at some point swing you in a playground, an actual physical playground. And I'm interested in, very loosely, I'm going to put it like this, describe this, describe/understand this system. And I want to do that from scratch, as if we were Greek philosophers, I don't know, a couple of thousand years ago, thinking how we could even approach this problem. Well, technically, we're going to use derivatives, and they didn't have derivatives. We're some time traveler Greek philosophers in here. So the first question that I want to ask you, and this is going to not be a monologue, but a multi-log. What do I mean by describe and understand? What do you think that means? Try to shoot into the microphone so that
you talk about like if you know what the system looks like now, what would it look like X seconds from now or something like that?
So a very big word that I'm going to put in here is predict. I want you to be able, exactly as you say, if I tell you my system is now here, how it's going to be later in time, how it's going to evolve. Yeah. So the dynamical variable that is controlling the flow of this is time. In this case, I am interested in understanding how the system behaves as time progresses. Now, that is not always the case. For example, if you're trying to solve a stationary problem, like the heat equation, you might be interested in asking yourself, if I change the boundaries of my metal plate to be on this specific temperature, how is the solution going to evolve as a function of space? You're looking for a steady state thing. So you already assume that time is not passing. I just want you to keep in mind that not every system that we study, the dynamics is driven by time. Sometimes it's driven by something else. And in general, we're interested in some controlling variable that I can change. How do the important response variables of my system change with respect to that? And spoiler, we're going to describe that through a differential equation. Excellent. Now, that is what I mean by describe and understand. What is a system? What exactly I'm trying to describe as a function of time?
The motion of the mass as it moves along the pendulum.
Fantastic.
For the position.
Perfect. So motion of the mass. So in this, we're going to start thinking about something that people call degrees of freedom. What exactly I'm describing here? We can make approximations as physicists and say the rope has a mass, the rope can stretch and compress. I'm going to approximate that as something that is not the most important part of my system at this moment. So for all intents and purposes, one way of describing this is just imagine that the rope is almost a stick that is not compressing or stretching, and that it doesn't add mass to the system. So in principle, I only have one thing that I'm interested in, which is the position x as a function of time and y as a function of time or of this mass. Make sense? Everybody agrees that with these simplifications, there is nothing else that I could describe for this system. For example, somebody could say, well, maybe when the thing is doing like this, friction takes in and the mass starts heating up by interacting with air. That is true. That will happen. I don't care. For now, let's just simplify our life a bit further so that we don't have to think about that. Everybody agrees that these two are enough quantities to describe the system for what we are discussing today in this classroom.
Yes.
Excellent. Do I really need two quantities? Think about it a bit. Are these two friends independent, x and y? In particular, if my thing is moving, I'm going to try my best to do an arc in a trajectory that looks like this. Can I change y without changing x?
No.
There is some constraint. There's something that is linking these two together. And that literally has a name, constraints. That will appear later whenever we talk about Hamiltonian dynamics and Lagrangians and all of that. But for now, it's sufficient to say, Pablo, you're right. These two are enough, but they're too much. Maybe I can describe how the system evolves using another coordinate, another degree of freedom that is only one. Well, can you help me with that? What do you think I could use? Daniele.
Theta.
And what is theta?
The angle between.
So Danielle is suggesting, I can use a third, for now I'm going to call it a third coordinate. This is a third number, which tells me the angle that this thing is doing with respect to the vertical. Again, theta is not independent of x and y. I cannot change theta without changing x and y and vice versa. But if I give you, and this is a way to think about these things. This will be very important later when we talk about Lagrange. If I give you, for a given time, I give you the value of theta, can you figure out the other two? Especially if you know that the length of the rope is L. For a given theta, x and y are completely determined. So x and y are redundant if I give you theta. So theta, thank you so much, Daniele, is a perfect coordinate to describe this system. There's nothing else that the system, as we have described so far, can do that I cannot encapsulate or understand through theta. Everybody's happy? Makes sense? Yes? Some folks? Make sense? I haven't heard you in a while, so I get worried that the connection dropped. You following me? Can anybody say a yes?
Yes.
Excellent. Thank you so much. All right. So what is my objective? My objective then is to describe theta as a function of time. If I can figure out a function that tells me that maps time to angles, I am done. Game over. I am got with respect to this problem. I can describe anything that there is to describe to this. How do we obtain an equation to describe theta as a function of time? What do you folks say?
We start with defining what would be responsible for changing theta.
Very good. What do you think that will be? And you can use previous knowledge. If you already remember something from your undergrad, you can shoot it. Do you have something that can tell you how theta will change? What will drive changes in theta?
Forces on the mass.
Forces on the masses. Make sense? Right? So if you use Newton's equations, what you will have, my goodness, this is a bit crowded. Let me move. Okay, no, let's make another diagram here. You have your system in here. And you can think that you have two forces acting on the system. The force of gravity, that is going to be mg, and you have the tension of the rope. And then your thing is swinging in this way. Now, Newton's, so maybe I got a bit ahead of myself. I'm talking as a theta as a function of time. Newton's equation talks about the forces as vectors, meaning the force as a vector is going to be equal to the derivative of the momentum with respect to time, which in this case I have a constant mass. So this is going to be m times x. Let's put it as an r dot dot vector as a function of time, where this friend is what we were describing as x as a function of time and y as a function of time. But we want to describe this in terms of theta. Now, when we talk about Lagrangians, this thing becomes extremely easy because you can make equations for generalized coordinate. That's what you can think of theta. In this case, what we'll have to do is to think what exactly are the forces that are acting on this particle and try to come up with an equation that involves theta only. I'm going to, hello.
Hi.
I'm going to skip that step for a bit because I want to focus on the solving the differential equation. But basically, if you write the force as the two components of the tension, you have a component in x and you have a component in y, and then you have the component in y only for gravity that is pointing downwards. You will arrive at two equations that relates to the movement in x and y, and you can extract an equation for theta. The final equation that you will get for theta, once you go through that, and I promise we're going to do this when we come back to classical mechanics, but I want to focus on the math part now, is something that looks like this. Two derivative of theta with respect to time plus sine of theta with respect to time times g over L. You think gravity is stronger? Yes. This should be equal to 0. Let me check. Yes, we got the right equation. So after you go through all that process, hooray, you got what you wanted. You got your differential equation that tells you how theta is going to change with respect to time. Make sense? And these are the rules of the game on how this angle is going to change as, again, as I said, as time progresses. What do we have to do now if we want to be able to claim that we have solved the system and we can describe it? What do I need to do? What are we after? And this sounds silly, but I have faced a lot of people, me included, where halfway through you are kind of lost and you don't know exactly where we're going. What I'm trying to get.
Theta of t.
Theta of t. Do I have theta of t after I have written that? I have to solve for it. I still have some work to do. And that takes us back to the previous class when I was discussing why differential equations appear so much. Is because as physicists, as scientists, we're really good at describing small changes in things. I can tell you the rules. I cannot tell you directly, oh, by the way, theta as a function of time is this. So that's why after we did all the physics, or half of the physics, because I didn't want to go through all the derivation, we ended up with this equation. Now we have to talk with our mathematicians friends and find a way of obtaining theta from that equation. Most of the time, you're screwed. You cannot do that by pen and paper. Most of the time, a computer has to do it. In this case, we can do a good approximation. So now, my question for you all, does this equation look like any equation that you have solved so far? You remember the two differential equations that you were tasked to memorize?
That looks like the second one.
Kind of. Can you tell me how the second one looked like?
Wait, maybe it does. No, it only has sign in the solution.
Can you just tell me what you?
Oh yeah. The second derivative of t is equal to the negative function.
So if I have this equation.
Yeah, second derivative of the function with respect to t.
Right?
Yes.
And we allow to have a constant here that I'm going to call omega square. Remember that we discussed about the square, the 4, the blah, blah, blah. Does this equation look like that equation? If you change f for theta. Why yes or why not? Some people, please unmute yourself at any moment that you want to say it. What do we think?
Not quite, because you have the sign in there.
Oh, that makes me so happy. Good job. I'm going to highlight the troublemaker here. This sine function, I do not have that function anywhere. You see that to some degree, I could identify this omega square with this g over L. That is just a number. So in principle, these two things are kind of the same. I do have my second derivative. And see that once I pass this sign to the right, I'm going to get a minus sign, which is the same minus sign that is on the other side. That gives me hope. But I have a sign function in between that I do not have on the previous equation. And that spoils everything. Is there anything that I can do to get away with kind of mapping this equation, the equation that we already know how to solve? Any ideas?
As long as theta is small, sine of theta and theta are pretty close.
So Cooper is saying, well, maybe I don't have to go with all the trouble of thinking about the function sine. I can approximate sine, like how an ant will look at sine. And this is what you probably have heard it in your physics classes, the small angle approximation. If theta is very small, the function sine is indistinguishable from the function x, the function that is just the argument that is inside. So long as theta is small, I can grab all of these and say sine of theta as a function of time is approximately theta as a function of time. If I wanted to get slightly more precise, what would be the next term? Do you remember? In the Taylor series of sine? The first was a linear term. Sine didn't have any quadratics because quadratics are even functions and sine is odd. So how will the next term look like? X cubed times something. So the next will be something times order theta cubed. So if theta is really, really small, let's say 10 to the minus 3, theta cubed is 10 to the minus 9. Of course we can neglect this thing. Makes sense. Are you following? I don't know how many of you saw this in undergrad, but I remember the first time that I was showing this and I was so confused because it's like, what is happening? Why are we, this is what it meant. So now we end up with an equation that looks like theta, second derivative of theta with respect to time is equal to minus g over L theta as a function of time. And what is the solution to this equation? Let me ask Zoom folks. Can somebody from Zoom help me? So you also participate. Do you remember? A function whose two derivatives is the same as minus a number times a function. If you don't, you can say I don't, and that's okay. Fair enough. Room people.
Cosine of roots g over L t.
So, perfect. My recommendation, the first thing that you say, sines and cosines. The details comes later, but I really want to make your neurons fire in such a way that you see that equation, and the first thing that comes to mind, the details of matter, is sines and cosines. How is going to look the solution? You do this, a sinusoid, that makes me extremely happy.
Sines and cosines.
Excellent, fantastic. So wait a minute. I'm going to put it in here. Sines and cosines. Exactly what sines, what cosines, we're about to figure that out, but that's the first answer. Okay, now tell me, which sines and cosines?
Cosine of root g over L times t plus the sine of root g over L t. And some constants in front of that.
Fantastic. Very good, yes. That is very important. G over L. G over L. And some constant that I'm going to call A and B. That's it. That is a solution to this differential equation. Why do I need the two constants? Do you remember the game that we played last week where you integrated a solution, you integrated a boundary condition, you integrated an initial condition? I told you, by the way, the function at 0 is 1 and the derivative is 1. You need these constants to know numerically how the solution is actually going to evolve as a function of time or as a function of x in this case. Make sense? Actually, last week, I gave you the value of the function at 0. I didn't have to give you the derivative because you could figure out the derivative from the differential equation. In this case, since it is a second-order differential equation, because of reasons, I need to give you two numbers for you to start propagating the solution as a function of time or x or whatever. Make sense? Anybody's lost with respect to this? Do you follow? Any questions, any comments? One of the things that confused me a lot when I was in undergrad is the unfortunate situation that this is a sine and the solution involves sines. And that is just coincidence. Don't confuse one sign with the other. The first sign is a sign that is there because of the rules of the differential equation. Once you simplify it, the solution ends up being sines and cosines. But it always confused me. When I saw sine of theta, I was like, oh yeah, of course, because of the sinusoid. And I said, no. I could have put an arctangent in there, something that also has a linear response around 0. The solution will still be sines and cosines for small angle approximation. Make sense?
Yeah.
Fantastic. I'm so happy. Okay, let's go to our second example. Harmonic oscillator. So I have a particle with a spring. And in the previous iteration of this class, I actually did this experiment, but today I decided to focus on something else for the class activity. But if you look at the old videos, you will see me playing with a spring and a pendulum. You can actually do one of the extra homeworks that I put in there, which was try to write a Python code that traces the trajectory of these things and plots it as a function of time. Coming back to the present, I have a mass m, and I want to describe this function as a function of time. What does that mean? Sorry, describe this system as a function of time. What I'm after?
Motion.
Equations of motions for who? What I'm trying to describe? How the block moves as a function of time. What will be a good set of coordinates to describe what happens to the block as a function of time?
Y.
You're asking or you're saying?
Y. No.
It's
The letter Y.
The letter y.
Yes, Y is a function of t.
So I could put this y. You had other thoughts?
No, just that. To me, it's a one-dimensional system.
In reality, this will be a three-dimensional thing. The thing can have a y, can have an x, and it could have the other one. In principle, but I have not said that, and we are all trying to do simplifications in our life. So let's imagine that this is a one-dimensional spring. We're not allowing it to move left or right, and we're not allowing it to move out of the board. But in principle, it could. And you could be interested in models such as system. I have one of my best friends, well, my best friend works in the LIGO collaboration that detects gravitational waves, and they have pendulums. And they have to be extremely careful on what the pendulum does whenever it vibrates, because there is a truck passing by a couple of kilometers away, and that involves coupling degrees of freedom of the pendulum doing this, and doing this, and doing this, and it's a mess. For now, we don't have to worry about that. All right, cool. So now what? How do I obtain y as a function of time?
Think of the forces on the mass.
So the pathway that I would like to embrace in your minds is, I need an equation for this thing, probably a differential equation. Probably I can build a differential equation talking about the changes on this thing. That probably has to do with forces. That's probably a Newton equation. You see, that is a reasoning. It's your reasoning. It's exactly what you were thinking. But I want to formalize step by step such that whenever somebody asks you this, you really think like a physicist. Is, Newton is my friend. It's not something that I have to solve because in class people told me. Make sense? So I need to figure out the forces so I can write a dynamical equation for this quantity as a function of time. What forces are acting in here? Same old gravity, mg, and then the restoration force from the spring. And a good way of modeling this doesn't have to be the case, but is to say my spring has a spring constant k that tells me how angry the spring gets whenever you perturb it around its equilibrium position. So the equation of motion is going to be the forces acting on my system is going to be proportional to my dot as a function of time. And in this case, the forces is minus mg plus the restoration force that is k y squared. Yep. Over m. Yeah, I complicated my life. This is very annoying. I'm going to change problems because I don't want to have to deal with that g. I'm going to put this right here. This is the box of Pablo didn't prepare his class that much. And we're going to make a similar problem. Bear with me for a second. Now I have a one-dimensional, let me use the same spring as well, but this friend is going to move only in the x direction. I don't want gravity because gravity is a linear, is going to be annoying. I will have to absorb it somewhere else. So just let's change it a little bit. Now I have this friend that is moving in an horizontal surface, has no friction, and I'm trying to describe how it changes as a function of time. Make sense? What coordinate can I use for this? Now that you're all experts, x as a function of time. Yep. So I write my differential equations. All the forces acting on this x is going to be proportional to mx dot dot. And in this case, what is the only force that is acting on my mass? The spring. No gravity, because that will be annoying. So I'm going to say that this is proportional to k x squared. People usually put a 2. Do we want a 2? No, it's a force. Sorry, not squared. Yes, thank you so much. So if I put it like this, I'm going to be in trouble because the further out the mass moves, the further the force pushes to go in that direction. So thank you, Josh. If I put a minus, now it's a restoring force. Now it's something that if you go very far away, I'm going to ask you to come back. And if you start going to the negatives, the force is going to switch signs so that it pushes to the positive. Make sense so far?
Mm-hmm.
All right. Now, is my job done? Have I solved my problem? What do I need to do now? Excellent. I need to find the solution of this differential equation. So I have, let me put it in a single one. This m plus k over m x of t is equal to 0. And I ask you, what is the solution to this differential?
Sines and cosines.
Muy bien. Excellent. Fantastic. Yes, sines and cosines. You literally trigger an emotional response on me and I switch to Spanish. Sines and cosines. It's the exact same thing as the previous one. In this one, I'm not making an approximation though. So this is exact. How exact it is with respect to the physical world is another story because springs actually deform. That creates hysteresis. It's a mess. But for the mathematical problem that I'm set up to solve, this is sines and cosines. And you know how to write the equation. I'm not going to write the solution. It's sines and cosines with a frequency that is going to be the square root of this number. So you see, in the pendulum, it was this ratio that controlled how fast the pendulum was oscillating. In the spring, it is this ratio that controls how fast the pendulum is oscillating. And it's interesting. If you look at the other one, doesn't involve the mass. In principle, you can hang something that weighs a lot or weighs a little bit, and it will not change the oscillations. That's because the inertia and the force both are proportional to the mass. In this case, the force is not proportional to the mass, the inertia is. That's why the mass appears. Now, you will see this equation a lot. This is called the harmonic oscillator equation in classical mechanics. You will actually see it in quantum mechanics a lot. We're going to have at least 1 or 2 classes just devoting to solving the quantum harmonic oscillator. And I ask you, why? Why is the case that this type of equations appears so much in science and engineering, both on the classical realm, but also on the quantum realm? Any thoughts? It's a difficult question. I don't expect you to have a full answer, but I want you to think. So for me, there is 2 answers. The first one is silly, but it's one of the few problems that we can actually solve by pen and paper. So we really like to show off to our students, look at how I'm able to solve the harmonic oscillator, both in quantum mechanics and in classical mechanics. Seriously, though, it illustrates some ways of approaching problems that are helpful for more challenging one later, but in this one, it's easier to see. And you will see it in the quantum one. When I first took quantum mechanics, I was super confused and I didn't understand anything of what the professor was saying about the quantum harmonic oscillator. I don't know if that is the case for you. I will try to make it more accessible. But you will see that many of the properties that we look in there in terms of the creation and annihilation operators makes it easier to understand more complex things that come down the road. And in the case of classical mechanics, many problems, and that comes into my second reason, are going to be very easily to approximate to a harmonic oscillator. By that I mean, you can have a now real physics case in where you have a particle x, a particle, with mass m that is interacting through some coordinate x as a function of time, and you might have a potential v of x that tells you how much the potential energy changes with respect to changes in this coordinate. In the case of the harmonic oscillator, this looks like a parabola. You see it here. The force was the first derivative of the potential, so it was linear in x. The antiderivative of x is x squared, and that's why the potential looked like a parabola, and you basically had the harmonic oscillator that was bouncing back and forth in that thing. In real life, it will never look like that, but it might look like this. And then you say, this is an extremely complicated function of x. I have no idea what is the solution, the general solution to the differential equation, blah, blah, blah. But if I ask my x to be around this minima, x0, and it doesn't go too far away, nobody will convince me that I cannot approximate this by a parabola and solve the problem in the small perturbation approximation. In the case of the pendulum, that was a small angle. In the case of anything else, it will be small oscillations around a position of equilibrium. That's why this appears a lot. In quantum mechanics, it gets even more tricky because, well, these are wave functions instead of trajectories, but it's the same idea. You will have an ammonia molecule that can oscillate. One of the atoms can oscillate with respect to the other 3. How does that happen? Completely analytically, it's hard to describe. If you make an approximation and you treat the thing as oscillation around the equilibrium system, it's going to be much better. Make sense so far? Okay. Any questions? Some folks?
Nope.
Okie dokie. So that takes me to this class activity. Let me share my screen again. And after that, we're going to take a 5-minute break. I actually have to go, while you're going to be working on this, I have to go to find the arrows because I didn't have time to find them, but they're in the next room. Okay. Can you see my screen, some folks?
Yes.
Excellent. So here is your, and Josh, I'm going to ask you to, I don't know where, give it a try. Are you connected in Zoom?
Yeah.
Okay. find a room and discuss with the two Zoom friends for the next 5 minutes. People in person, I recommend that you pair in groups or the whole crowd. You have 5 minutes. I want you to try and solve that. By solve, I mean you have a second order differential equation on F. I'm giving you the numerical values in there. You have region 1, region 2, and region 3. The different regions are because the potential d of x is a piecewise function. So that means that has different values at these different locations. What I want you to do is to look at region 1 and figure out how the solution will look like. Look at region 2, do the same, and look at region 3 and do the same. If you're able to, you can try to make a drawing. The solution should be continuous across boundaries. And if you really want to solve this problem, it involves a lot of numerics that I don't want you to do because you will have to solve some transcendental equations and yada yada. I will show you how the solution looks like after, but I want you to at least start thinking, how do the three solutions in the three regions are going to look like? And if you can, make a drawing, connect them, make them more or less continuous. We're going to look at it together in the next 5 minutes. So it's 2:17. I'm going to be out solving this problem with the arrows, and we reconvene at 2:22. Give it a try and have a nice discussion. All right. So friends, let's have the discussion. I realized that this was very little time to do these things, but otherwise we're not going to have time to do the projection, which I really want to do. Tell me, I'm going to start with some folks. What are your thoughts?
In the first region, the
Mhm.
solution will be sines and cosines. Since
How do
you're,
you know it's sines and cosines?
when you plug in for v of x and e, you will get 2.5 on the right, but then you'll need to put the negative sign on the right also. So the negative will indicate the sines and cosines.
Let me put in here speakers. Now I should be able to control it better. That makes sense for in-room folks? Yep. So basically you play that v is a constant in any of the regions. So the equation always looks like f prime prime equals a number times f. And that number changes signs depending on where you are. So room folks, what would you think the solution should look like in region 2?
We recognize that it had, you said like f prime prime plus some number times f.
F prime prime equals a positive number
Right,
times
in this
f.
case, yeah, this one is positive.
So what is the solution in there?
Not sines and cosines.
Excellent. That is an equation that you have not encountered yet. I have never told you that this is not artificial intelligence, but natural intelligence. You're able to generalize. So what is the solution in that case?
Usually I think you end up with something that's exponential, either decay or growth, depending on
Make sense?
other things.
Yeah, because if you think of what was the equation for the exponential we first said, f prime equals number times f.
Yeah.
You make a second derivative, you have the f prime prime equals a positive number times f, because the number is squared.
Okay.
And now you're allowed to have e to the plus x, and you can also have e to the minus x. So that is the growth and decay that you're talking about. Make sense? Do I have both solutions inside there? So I should start. Let's take a picture of this so that I can type. 1 second. So basically, the solution in here should look like a times cosine of something x, some frequency, plus b sine of something x, the same frequency, and the frequency is going to be given by the subtraction between this number and this number, so 2.5. The solution in here, we said, should look like e to the plus something x and e to the minus something x. That something is the subtraction of those numbers as well. Do I have these two numbers? Do I have these two functions? I'm going to put in here a c and a d. Should I keep both? Because I think I heard some of you saying that I should only keep one of them. Was that the case, or I misheard?
We mentioned that it would probably just be decay.
Why? Okay.
That's the way it's shaped, I guess.
So here's the thing, and we'll talk in this more detail later. The differential equation doesn't care. You look at the differential equation, and the differential equation, both solutions are valid. So in principle, you should have both. As a physicist, though, later on, if the region 2 extended up to infinity, you will feel very uncomfortable. In this case, by the way, this is the wave functions of a particle we're solving Schrodinger equation. You will feel very uncomfortable that your solution just grows and grows and grows. So you will chop it. You will say, my boundary condition at infinity is that my particle should, the wave function should decay, not grow. But in this case, that region is finite. There is nothing wrong with having an exponential increase or an exponential decay. Both are allowed, and you will need both if you want to make your solution continuous with a derivative that is also continuous. So in principle, it's both. And in the case that I'm going to show later, is also both. Make sense? What about region 3? What should be the solution in region 3?
0.
Why 0?
I don't know.
Sines and cosines, because it's still that negative.
Sines and cosines.
Thank you. So happy. You see, V is 0, but you still have that E times F. So you have D sines and cosines differential equations. F prime prime with a minus equals a number times F. That's it. Sines and cosines with a higher frequency. So if you had to draw a function, how will the function on region 1 look like? Sines and cosines. How will the function in region 2 look like? Well, some exponential, some exponential growth in some sense. And how should the solution look outside? Exactly, sines and cosines. So this is a solution to your differential equation. Later on, depending on what you meant in the quantum sense, you might want to turn on or off some of those parts, but in general, that is how it's going to look. And let me share with you, because I made a nice Mathematica code just to illustrate that. And so I put these to 3, these to 3. How much did we say the height in region 2 was? In region 1, sorry, it was around 2. In region 3 was around 5. And my energy was 4.5, I guess. And this is how the solution looks like. If you start with the value at 0, derivative 1, you do your shooting method, which now you're all experts. You know how to make this if you needed to. And your solution in the inner region looks like a sines and cosines and some exponential. In this case, see that it's mostly an exponential growth. And then you have sines and cosines outside. If you mess up with things in here, like, for example, the energy of your particle or that number that you had in there, different things happen. If, for example, that energy is bigger than that barrier, it's sines and cosines everywhere, just with different frequencies. And anything in between will give you some interesting behavior that we call resonance. You see the transition that happens between these two things where the function outside is very small? That is a resonant, quantum mechanical resonance state, where the particle is unbound, but it spends a lot of time inside. So it's a quasi-stable system. Doesn't matter, details, but it's a cool animation, and I wanted to share it. Okay, so now I am extremely behind schedule. Still, we're going to have a 4-minute break. I will see you at 2:36, and we're going to talk about vectors. We're going to start with linear algebra, and we're going to do the projections. So see you in 4 minutes. So we are going to talk now about linear algebra as an introduction. I don't think I'm going to be able to cover all of this, but that's okay. I will see you on Wednesday too. So the first thing that I want to do, as we usually do in these classes. Some people, can you hear me, by the way? Can you confirm that again?
Yes.
Excellent, fantastic. So the first thing is vectors. What are vectors? What comes to mind when I say vectors? I'm going to take notes of all the interesting thoughts you folks have. Tell me.
Direction and magnitude.
Direction and magnitude. You say that, and I have flashbacks to my high school physics teacher that was chasing us, just trying to make us remember that. What else?
Arrows.
Nice.
Very nice. I like that. Arrows. What else?
Like a one-dimensional matrix.
Yeah.
Like one.
Yeah.
Yeah.
It's strange because it's not the dimension, because I can have a vector that is 7 dimension.
Yeah, I don't know what's the math like a 1/7.
Yep.
thing,
Yep.
but I don't-
Uh,
One dimension in one.
I'm going to put it as flat matrix. And then we'll have to think what the heck a matrix is. But yes. What else? Anything else? Whenever I think of vectors, I think of functions. Because as we will see later, functions, like sines of x, you can think of that as a vector, and it's super powerful to think it that way. Anything else?
What's the thing called where it's like a graph and it's showing a function with all the different vectors at each point? It's like
Like a vector.
Like a vector
Is it a
field,
vector
you're
field?
thinking? Like,
is there another word for it? Like
A graph of arrows.
a
is that what
topographical map?
you-
Like
I
think it's a vector field.
Yeah.
a vector
don't know. We're just throwing out
maybe
words.
you're thinking of the gradient of a surface, perhaps, that has all the arrows.
Yeah.
Okay, I'm going to put vector field. I'm going to put angles. I like to think about angles. You know, you can ask the angles between vectors. That is going to be important later. Very good. I'm going to also put representations. And we'll talk about those later. But for now, for the discussion that we're going to have, I want you to think of vectors as arrows. And there is one context in where these things are very useful for many reasons. Particularly whenever we're describing dynamical systems, we talk about how the position vector changes as a function of time. I might be tracing a particle. For example, if I was tracing the spring harmonic oscillator that was vibrating, and my spring is here, my coordinate system is in here, this thing is going to be doing this. If I was tracing a pendulum, this thing is going to be doing this. So vectors are a natural way of expressing the changes in coordinates of systems that I'm trying to understand dynamically as they change in function of time. That's one of the reasons they appear a lot. Another very simple place in real life where they can exist is, imagine that you're in a city. We're in the city of East Lansing, and my coordinate system, I'm going to base it exactly in this room. This is BPS. If I want to do this correctly, wait a minute, this doesn't work. I need to put this in here. All right, there we go. And yeah, more or less. So imagine that I have my coordinate system. This is BPS. This is north, and this is east. And can you repeat me your name? Gabby? Gabby. So we want to help our friend Gabby. That is your first week at MSU? Have you been to the dairy store to eat ice cream?
No.
We need to solve. I cannot take you all today because I have a cake with a student that is leaving. But maybe Wednesday we can all go to the dairy store together after this class, and it will be my treat. I will be more than happy. But we have to take you there. It's amazing. Super cool ice cream, the best ever that you have ever tasted. If we wanted to tell you how to reach there from a coordinate system, from a map, how can I tell you how to go there? I could say, imagine that you're looking at the map from above, and this is BPS. And here's the dairy store, and I'm putting it as a pink blob. a cloud where dreams come true because it's really good. And if I want to tell you, you have to go in that direction, I can just make a red arrow. And now I got really excited. We're all going for ice cream on Wednesday. So I have my red arrow that is pointing. Actually, can I do this if we are, where is north? I think north is that way. So it's an arrow that points there. If you walk straight in that direction, you will find it. This is useless if you really want to find the thing. You cannot pass through walls. You don't know how long you have to walk. So I'm going to call this vector v, and I'm going to try to express this in a coordinate system that is useful. For example, a coordinate system could be x and y. I have my x vector and my y vector. Let's put different colors. Let's see how complicated we can make this. Y, I'm going to put it in orange and x in green. So I can say this vector v is going to be equal to some number. I'm going to put it as a in the direction x hat plus another number. We're going to put it in, do I have another yellowish brown? So number b in the direction y hat. This is basically telling you, Gabi, you're going to walk, I don't know, 150 meters in the minus x direction or west, and then you're going to go south or in the minus y hat direction for 20 meters. And you're going to arrive at your destination. Makes sense? Yeah? So these two friends are my basis vector. And these two friends are my coordinates. In that basis. Yes? I could abbreviate this and say my vector b is equal to AB. Now, you can only do this between friends. The person that is reading this has to be able to understand that what you mean by AB is A in the x hat direction and B in the y hat direction. If you're not friends with that person and you have never talked to them and you just write AB, they have no idea what you mean by this. Does that make sense? So these two numbers, that in this case is going to be, to my best estimate, minus 150 meters and minus 20 meters, only make sense in these bases. There's another representation that you could do of this vector that is more useful if instead of giving directions in a city, you work in an artillery corps of the army or you're trying to bomb the enemy. You don't necessarily want to tell them, you're going to put the cannon in the direction this many in X hat and this many in Y hat. A more natural system will be this angle and this far away is where the enemy is. So that's how you want to aim in there. So I could represent the same vector v as a number r in the r hat direction. To be consistent, let's put this r hat in deeper blue. What does this mean? Well, you're going to grab the vector r hat that I'm putting in here. This is r hat. So basically saying, if this is x hat, measure an angle of this amount until you point exactly in the direction that we were talking about, and you're going to walk there 170 something meters, and you have arrived at your location. Yes? Now, there is a piece of information in here that I'm not putting that is extremely important. This r hat points from the origin to wherever I'm interested in you walking. That depends on the angle theta. Put it in red. So to tell you exactly where the data store is with respect to us using this coordinate system, I still need to give you two numbers. Which are those numbers? It's a non-rhetorical question. What are the two numbers that I have to give you in this coordinate system?
A and B.
That is for the Cartesian one. What are the two numbers that I need to, if you want, literally think it as an engineering problem. I have to tell you how to walk there using this r hat idea. What are the two pieces of information that you need to know to unequivocally know where I'm pointing towards you to go?
R and theta.
An angle, so that is x. Move 195 degrees. And then how long do I have to walk? Sorry, yes, you have to walk 175 meters in that direction. Does that make sense? And if you're between friends and people know what you're talking about, you can write this as, it's less common, but you can definitely write it as r theta. And the person will understand what that means. It's not r in the r hat direction and theta in the theta hat direction. It's just telling me the two numbers that I need to reconstruct that position in space. Does that make sense? Very good. See that if I were to even use a different basis that is still Cartesian flavor basis, two arrows, two bases that I'm going to write it as a basis vector, I could rotate with respect to x hat and y hat and find something else. My coordinates will change, the numbers will change, the vector will be the same. So if I were to write, I'm going to make another diagram because this is getting very messy. This is my original one. And here was x hat and y hat. And here was my red arrow that was pointing in this direction. We found an A and a B that were corresponding to x hat and y hat. But if somebody comes and says, actually, I want to use this basis vector, phi 1 and phi 2, the coordinates that I will use to represent B in that basis will be slightly different or very different, depending on how much these two things are rotated. And that's fine. Make sense so far? Yep. Okay. We have 12 minutes to do the activity. We're going to try our best. I want to ask you, let me go back to this thingy, and I'm going to reverse the arrow so that it's looks more positive. This is my vector B. And what did I put for the colors? Okay. This is x hat. And this is y hat. And this will be the coordinate A, the number A. Do you see it? And this will be the coordinate B. That I can repeat in here if I want just to. Yes? I'm interested in obtaining these numbers. Suppose that I gave you the arrow. Can you think of any way of engineerily obtaining these two numbers? It will make more sense when we do the activity, but I just want you to think about it.
I'm getting A and B. Is that what you're asking?
I would like to obtain A and B. If you want, and I'm going to, it's hard to show, but basically, if I had a physical arrow and the coordinate system, how do I measure A and B? How much this arrow has a component in X and has a component in Y. If I want to physically measure this object, because usually in problems, people give you, this is A and B, do this calculation. No, I want the inverse thing. I want to give you the arrow physically and for you to be able to find those components. What
You
can
measure the angle?
You can measure the angle. Very good. And then what? You use some trick things. Excellent idea. Suppose you don't have a protractor. I do have one there. But if you don't, what else can you do? What about this idea? You want to comment?
I was gonna say, can you measure the arrow? Do you have a ruler?
Yes, I have a ruler. Okay. I can measure distances, but I cannot measure angles. Because with angles, I will be able to solve it. What if, with a ruler, you could measure the arrow? If you were able to put a flashlight or a lantern here, and you shine some light, and you have to do it very carefully. It has to be light that hits it exactly perpendicular. The shadow of this arrow in the x-axis is going to be exactly that length. You can measure the shadow. And then you can do the same thing with y. And I will give you what those coefficients are. So the keywords in here is shadow or projection. You're going to project this vector into the x direction, measure that, and you're going to do the same in y. And that's exactly what we're going to do right now. So soon, folks, this is going to be challenging for you to see. I'm going to try my best because I'm going to turn off the lights, including the projection. Let's see how that works. Apologies if it doesn't look very well, but once I have the recording should look better too. So I'm going to need the help of some people. Who wants to be the lantern? So what we're going to do, by the way, do you mind being recorded? Okay, excellent. I need to ask that in advance. Please help me, or I'm going to get in trouble one. So I have my arrow here. My arrow here measures exactly 1 meter. And I am going to use a protractor to put this exactly at, as best as I can, at 60 degrees. So then the question will be, if I were to have this, can you try to visualize from the drawings that I was making, the two components that I will have? I will have a X component and I will have a Y component. Does that make sense? Yeah? So you're going to go first. Here's your ruler. And lights off. Lantern, can you help us? Aha. Oh, look at that. Very nice. So how will we do this? I need to be very careful that I don't screw this up. So if I do, I guess this, I need to make sure. How do we make sure that this is? Okay, can you do something? Can you actually come a couple of rows below? Because it's important that you're far away, but I think it's even more important that you're level with respect to me. So Gabby, I need you to come with me. You're going to measure this. Okay. Yeah. So this is far from ideal, but we work with what we have. Let's see. Can you put it a bit more high? Okay. Do you think that that more or less is perpendicular? Oh boy, wait a minute. That looks okay. Yeah, I think that will be fine. Okay, we're going to measure it, and if it doesn't work, I'm sorry. I'm doing the best that I can. So measure from, make sure that the 0 is in here. How much do you measure in there?
91.
Okay, can somebody remember that? Thank you, 91 centimeters. Can you give it to her? And now we have to measure, thank you. Now we have to measure X, I guess. Yes, so I guess if I flip it this way, I will be measuring X, right? Oh, so let me make sure that on top of everything, I don't screw this up. Okay, so I'm trying my best. Let's see how that works. The 0 is touching the 0 well?
Yes. Okay, here.
Okay, yeah, where my finger is. Yep. So how much?
45.
45. Oh. Yeah? Okay, so now, thank you. Everybody can go to your seat. Lantern, you did a fantastic job. You two did great as well. Thank you. And now we're going to turn on the lights. No, don't stop there. So that's what we did. That's how you can actually measure length. Can you tell me the numbers? So this was, in this case, this was 1 meter.
It was 91 and 45.
So A was measure.
Is that right?
91 point what?
That's what I had, yeah.
91 and 45.
91, and B measured.
You had it swapped because you did your X second.
I think you're right. Yes.
Yeah, but then the X is
Yes.
shorter
Yep.
than the
Yep.
Y.
So I think if we put it this way, it should be fine. It's just that this is 30 degrees, not 60. Yep. Sounds good, right? Later, estimate it with trigonometry, and let's see how. I don't expect the numbers to completely align because you saw, to actually do this projection, you need a lantern that is not only parallel, but infinitely far away, so all the lights come back. It should be close enough. And the important part is I want you to keep thinking whenever you're trying to find these coefficients, what you need is the shadow. And mathematically, the shadow ends up being proportional to dot products. Why? Because if you remember the dot product between two vectors, v1 and v2, if it's in 2 dimensions, this is equal to x1 times x2 plus y1 times y2. But this is also equal to the magnitude of v1, the magnitude of v2, times the cosine of the angle that they form, the magnitude being the length. That cosine, if the angle is very small, that means they make a big shadow with respect to each other. That means the dot product is going to be big. If they were to be orthogonal to each other, that cosine is going to be 0. Well, makes sense. The size of the shadow that one vector is going to cast onto another one that is orthogonal is going to be 0. Make sense so far? And we're going to think about, do I want to spoil this? I'm not going to spoil this. We're going to have this discussion next week. So let me switch to the playground that you're only going to be able to do one part of it. But next Wednesday, we're going to continue exploring what happens with this dot product and how we can generalize it to vectors in higher dimensions, and where thinking in terms of geometry is not as easy. But that's what we did today, and now you know how to do it. So to close, this is my playground. The second part has to do with this question about sines and the Taylor series. By the way, anybody thought about that? Do you think if the Taylor series of sine is the best polynomial that can fit sine between minus pi and pi? You gave that a thought. That's okay. That's the next playground. And as you see, it's not. In blue, you see sine of x or pi x. In orange is a Taylor series. And in red is what we can obtain with projections. We're going to basically find the shadow of the sine function onto the 5-degree polynomials, and we're going to find the best one. We'll cover that next class. The playground that I recommend that you try for next week, or in the next days, whenever you want, is solving that differential equation in there, where I have a potential function that is more complicated. You're not used to it. I don't think you can actually solve this by pen and paper, but maybe you can do some approximations here and there that will take you closer to a solution. Is the approximation that you have to do to say that x is close to 0? Is a question. What do you think? Should you try to say kind of the equivalent of small angle approximation and say that x is close to 0? I see some heads saying no. Why? Well, if you say that x is around 0, that is around here. And if you put your particle in there, it's just going to go down hills. Where is the particle going to make small oscillations? Under one of the minima. So if you come to this minima, you have to find who this minima is, and then you have to say x is around minus 1 point something, and small deviations around that number, and span your operators, span your differential equation using Taylor around there, and pray that the equation that you get at the end is something that you can actually solve, which you should be able to. Give it a try. Any further questions or comments before we close today? Some folks? No? Okay. You friends have been a fantastic crowd. Thank you so much for helping on the activity. Enjoy the rest of your day, and I'm going to see you on Wednesday, and we retake our usual room. Bye, some people.
Thank you.
Bye, Pablo.